It's hard not to be amazed. China's space program has once again achieved a major breakthrough. The Long March 10 has successfully completed the full controlled recovery of the booster stage of a heavy-lift launch vehicle. More importantly, this flexible offshore net capture and recovery technology is completely original to China. It is a brand new recovery approach that exists nowhere else in the world. So how exactly does this unique recovery process work? And why do we have to master rocket recovery technology? Let's first take a complete look at the entire recovery process. First, about 150 seconds after liftoff, the rocket completes first and second stage separation. The second stage continues carrying the satellite toward its planned orbit. After separation, the recovered booster immediately deploys its 4 grid fins and adjusts its attitude, turning the engine nozzles toward the direction of travel to prepare for the slowdown on the way back. When it reaches an altitude of 37 kilometers, 7 reusable YF-100 liquid oxygen and kerosene engines ignite for a second time at high altitude. Their reverse thrust cancels out the supersonic flight speed, while correcting the flight path at the same time, precisely targeting the recovery area in the South China Sea. The landing point error can be kept within 100 meters. The booster then plunges into the dense atmosphere and continues slowing down through the air resistance generated by the grid fins. Its attitude is adjusted automatically throughout the entire process to prevent an uncontrolled roll. As it descends to an altitude of 120 meters, the engines deeply throttle down and reduce thrust, bringing the vertical falling speed into a safe range. 4 sets of high-strength hooks at the bottom of the booster deploy and lock into position at the same time. They line up vertically with the recovery net as the booster slowly descends. The hooks firmly catch the net's main cables. The instant the booster touches the net, the entire cushioning net flexibly sinks downward. Combined with hydraulic dampers, it absorbs the huge impact energy layer by layer. Once capture is complete, the mechanical structure automatically locks in place. There is no hard impact during the entire process, leaving the booster with 0 structural damage. This approach is fundamentally different from SpaceX's Falcon 9 landing leg hard landing method. The Long March 10B completely removes the bulky landing legs and uses an original leg-free net capture system. First, this eliminates hundreds of kilograms of dead weight from the landing legs, which directly increases the vehicle's low Earth orbit payload capacity under the same overall vehicle size. Second, net capture provides a much larger margin for error. It is far more tolerant of directions in descent speed and landing position than a hard landing, completely eliminating the safety risk of the landing legs failing to deploy and the rocket tipping over and crashing. Third, flexible cushioning replaces a hard impact on the ground. Wear on the engines and vehicle body is extremely small, greatly shortening maintenance and reuse cycles. The supporting recovery platform is a dedicated recovery ship called Leader. It is equipped with a high-precision DP dynamic positioning system. Even in level 6 sea conditions, the ship's positioning error can be kept within 0.5 meters. Compared with Starship, which needs to return precisely to a land-based launch tower, the offshore recovery method is more flexible. So why do we have to develop controlled rocket recovery? It's actually very simple. In a traditional expendable rocket, the first stage accounts for more than 60% of the total rocket cost. After successful recovery and reuse, the cost of a single launch can be reduced by 40 to 60%. This can dramatically lower launch costs and strongly support the large-scale deployment of China's low Earth orbit satellite internet. Second, it also builds complete engineering experience in flight control and reusable propulsion for future crewed lunar missions, Earth-Moon round trips, and low-cost deep space exploration.